How do you build recommendation systems and search engines that, actually understand user intent instead of just mechanically matching keywords?
Right. Or how do you compress massive data sets, like squashing 100 complex features down to just 10 without losing the core information that actually matters?
Yeah, exactly. And how do neural networks and transformers automatically mix raw data to extract these hidden patterns that humans can't even see?
What is genuinely fascinating here is that while these sound like entirely different software engineering challenges, they're actually all solved by the exact same underlying mathematical concept. Every single one of these problems comes down to one fundamental operation: reshaping geometric space.
Welcome to the AI and ML YouTube channel by 60 Seconds Academy. Here we focus on practical and application-based understanding and concept clarification so that you can be industry ready and apply your knowledge to real industry projects.
And today is an incredibly important step in that journey. We're going to bridge the gap between abstract mathematical theory and the real-world engineering that powers modern artificial intelligence.
Today we're pulling from a stack of foundational ML textbooks, some recent research papers on transformer architectures, and our own engineering notes for this deep dive. Our mission is to answer one big question: how do machine learning models actually transform space?
Because that is where the magic happens.
Right. In our previous module, Module 3, we established a foundational concept.
Mm.
We learned that data points live as vectors in space. So if you are a Python developer and you write a list containing 3 numbers, mathematically you have just defined a coordinate in a 3-dimensional geometric space.
Yeah,
But today, we're exploring the active mechanics of machine learning. We're moving from the data itself to the engines that move and mold that data.
exactly. We are diving deep into the intuitive edition of linear algebra. And I want to be clear about what we mean by intuitive. We are not going to sit here and read formulas aloud or, ask you to memorize how to multiply rows and columns by hand.
Thank goodness.
Right. We are focusing purely on the geometric intuition. It is about understanding how these models rotate, stretch, and compress mathematical space to reveal the patterns that are completely hidden when you just look at the raw data.
Because raw data never hands you the answers directly. I mean, if you just stare at a spreadsheet with a million rows, the insights are buried.
Mhm.
So let's start unpacking this by moving from vectors to matrices, which is really the transition from static data to a transformation machine.
Yeah, let's set the stage.
Let's recap what we know. Imagine you are building a predictive system for a bank, and you are working with a customer vector. You have 3 basic features: income, credit score, and age. Say $80,000, a score of 732 years old. If you plot this, it's really just...
It's just a single point.
Exactly. It's a single point floating in 3D space.
Right. And as an engineer looking at a database, you see those 3 isolated values. But the fundamental limitation we face is that the single points, even when you plot millions of them, they don't inherently reveal the complex underlying relationships.
They're just dots.
Just dots. If you want to predict whether this specific customer will default on a loan, or if you want to recommend a highly targeted financial product to them, those raw independent variables aren't enough. We have to combine those features. We need to physically rotate the feature space, compress the dimensions to remove noise, and extract hidden, latent patterns.
And the mathematical engine that allows us to do that is the matrix.
Yes.
So if a vector is a point in space, what exactly is a matrix in this context? Let's strip away the dense academic jargon.
At its absolute core, a matrix is simply a machine that transforms vectors. That is the most practical, plain English definition you can hold in your mental model. You feed it an input vector, like your customer vector, and it processes it. It moves it through space and spits out a transformed output vector.
It functions exactly like a mapping or a function in programming. You pass an argument in, you get a return value out.
Exactly like that.
But geometrically, this function is picking up your data point and relocating it to a completely new set of coordinates. And the reason this is so critical for anyone looking to be industry ready is that matrices are the hidden engines driving everything in machine learning.
Literally everything.
They are the weights in your neural network layers. They are the mechanism behind linear regression. They are how we create embeddings. And they are the mathematical heart of the attention mechanisms in the transformer models that power tools like large language models.
When you read a headline about a new AI model having 70 billion parameters, it sounds unfathomably complex. But the reality is that the overwhelming majority of those parameters are just numbers sitting inside massive matrices. They're enormous transformation machines, waiting for you to pass an input vector into them so they can warp the space that vector lives in.
Let's visualize what that warping actually looks like. I want you to picture a perfectly uniform geometric grid of points. Think of classical 2D graph paper. Perfectly square boxes with straight grid lines running parallel to the x and y axes.
Now imagine what happens when a matrix is applied to that entire two-dimensional space. The grid itself changes shape.
The whole thing.
The whole thing. The matrix acts on every single point simultaneously. Depending on the specific numbers inside the matrix, that grid might rotate like a steering wheel. It might stretch out horizontally, pulling the points further apart. It might compress vertically, squashing the space, or it might perform a shear.
Let's define shearing quickly. If you take a deck of playing cards stacked neatly on a table, you press your hand on the top card and slide it to the right, the whole deck slants diagonally.
That's a great visual.
The bottom card stays put, but the further up you go, the further right the cards shift. The space itself tilts.
Exactly. And all of these movements, rotation, stretching, compressing, shearing, these are the physical manifestations of matrix operations. But this brings up a very strict rule, and it answers the question of why we call this linear algebra.
Right, because if we are just warping space, why can't we just twist it into a pretzel?
Because the entire mathematical framework relies on a specific constraint. Straight lines must remain straight, and the origin point, the 0, 0 coordinate, must remain fixed in place. After the matrix transforms the space, every single grid line that was perfectly straight before the transformation must still be perfectly straight.
So no bending.
No bending. Even if the grid is now slanted diagonally or stretched out 10 times its original width, the lines cannot curve.
If the lines got wavy or bent like a funhouse mirror, that would be a nonlinear transformation.
Right.
And while neural networks absolutely do use nonlinear transformations, like ReLU or sigmoid activation functions, those happen after the matrix does its job. The matrix itself is strictly linear. But let me ask you this. Why does the model want to stretch and shear this space in the first place? What is the practical engineering value of taking our data grid and slanting it?
It comes down to separating tangled data. Imagine you have two groups of customers plotted on your grid, the ones who faithfully pay their loans and the ones who default. In the raw original feature space, these two groups might be completely tangled up.
Like a mixed-up cloud of dots.
Yes, they might be clustered so tightly together that you cannot draw a simple straight line between them to separate the good risks from the bad risks.
They aren't linearly separable.
Precisely. A simple classifier algorithm looks at that tangled mess and fails. But if a matrix applies the right combination of stretching and shearing, it reshapes the entire space. It rearranges the geometric relationship of those data points. If the matrix stretches the space in just the right direction, those two previously tangled groups might suddenly pull apart.
That makes so much sense.
The complex, tangled patterns suddenly become easily separable. You can now draw a clear boundary between them.
So when I hear senior engineers say something like, the model is learning the optimal weights, what they are actually saying in geometric terms is that the model is testing out thousands of different ways to stretch, rotate, and shear the geometric space until the data finally untangles itself and the answer becomes obvious.
That is a perfect translation. The training process of a neural network is essentially the search for the perfect sequence of spatial transformations.
Okay, so if a matrix is reshaping the space for a single data point, what happens mathematically when we have dozens or hundreds of features interacting? How does the model actually compute that reshaping?
Well, this brings us to the concept of matrix multiplication.
Or what we should conceptually think of as feature mixing. I know that for many people, the term matrix multiplication induces a bit of anxiety. It brings back memories of memorizing arbitrary rules for multiplying rows by columns in high school.
The mechanical calculation of it can definitely be tedious, which is why we let PyTorch or NumPy handle the actual arithmetic. But conceptually, matrix multiplication is just a sophisticated mechanism for feature mixing. Think about our raw customer features again: income, age, and credit score. In reality, these variables are not entirely independent of one another. They interact.
Right, they influence each other.
Matrix multiplication is the mathematical operation that blends them together to create a more holistic, latent representation of the customer.
Let's use an industry-specific analogy here instead of basic math. Think of it like an embedding space in a recommendation engine. You aren't just looking at raw, independent metrics like number of times clicked and total watch duration. The matrix multiplication takes those raw metrics and projects them into a new space to create a composite, hybrid metric.
Exactly. Instead of viewing raw income and credit score in isolation, the matrix mathematically combines them. It might take 80% of the income value and 20% of the credit score and blend them into a brand new dimension.
A completely new feature.
Yes. We could conceptualize this new dimension as overall purchasing power. It is a latent feature, a feature that didn't exist in the raw data, but was synthesized by the matrix.
And let me challenge that for a second.
Yeah.
The matrix is just a grid of numbers. It doesn't actually know it's creating a concept like purchasing power, right? It has no semantic understanding of finance.
That is a crucial distinction. No, the matrix has no semantic awareness. It is blindly mixing the features based on the weights it currently holds. However, through the process of training and optimization, the model learns which feature mixtures actually help it minimize its error.
It just cares about the math.
Right. If blending income and credit in a specific ratio suddenly makes it much easier to predict loan defaults, the model locks in those matrix weights. We, as the human engineers, might look at that specific mixture and label it purchasing power, but to the model, it is simply the optimal geometric projection to untangle the data.
And this feature mixing happens at every single layer of a deep neural network. When you feed your raw data into the first hidden layer, that layer performs a matrix multiplication. It takes the raw features, mixes them up, and outputs new mixed features.
And then the next layer takes those.
Exactly. Then the next layer takes those already mixed features, and it mixes them again with a new matrix.
Layer by layer, the network is learning increasingly complex and useful representations of the original data. The first layer might just combine basic metrics. The 10th layer is combining complex, highly abstracted, latent concepts that we might not even have human words for.
And the mathematical operation driving this entire mixing process is something we actually covered in Module 3. It's the dot product.
The dot product is arguably the single most important mathematical operation in modern AI. To understand how matrices mix features, you have to deeply understand the dot product, because matrix multiplication is fundamentally just a massive collection of dot products happening simultaneously.
Let's bring back the flashlight analogy to really ground this. Imagine you are standing in a dark room holding a flashlight. The specific direction your flashlight is pointing is vector A. Now imagine there is an object somewhere in the room. The direction from you to that object is vector B.
If your flashlight beam points directly at the object, meaning vector A and vector B are pointing in the exact same direction, they are perfectly aligned. You get bright light hitting the object.
Strong alignment.
Right. If you point the flashlight slightly away, the object is only caught in the dim edges of the beam. The alignment is weak. And if you turn around and point the flashlight in the completely opposite direction, the object is in total darkness, zero alignment.
Mathematically, the dot product is the calculation of that alignment. It measures how much of vector A goes in the exact same direction as vector B. It outputs a single scalar number. If the number is high and positive, you have strong alignment, bright light.
It's a direct match.
Yeah. If it's 0, the vectors are completely perpendicular, meaning they share no directionality at all. If it's negative, they are pointing away from each other.
Now, connect this back to matrices. When a matrix multiplies a vector, it is systematically taking the dot product of your data vector against every single row in the matrix. You can think of each row in the matrix as a different flashlight, pointing in a different direction.
So the matrix is essentially shining multiple flashlights at your data from different angles simultaneously, checking to see which specific filters or directions your data aligns with.
Precisely. It is quantifying the geometric alignment between your data and the learned weights of the model. And this concept of alignment as relevance is the bedrock of the entire AI industry right now.
Let's look at how search engines work today. When you type a query into a search bar, the engine doesn't just look for matching text strings anymore. It converts your entire query sentence into a single, dense vector in a high-dimensional space. Meanwhile, every document, article, and web page on the internet has also been converted into its own vector.
To find the most relevant results, the search engine simply computes the dot product between your query vector and the millions of document vectors. It checks the alignment. The documents that yield the highest dot product scores are geometrically pointing in the closest direction to your query.
High alignment equals high semantic relevance. The brightest objects in the room get put on page 1 of your search results.
It is also the exact mathematical engine powering transformer models, which are the architecture behind large language models. The famous attention mechanism in a transformer is driven entirely by dot products.
Oh, that's right.
The model creates a query vector for a word you just typed and compares it against key vectors of all the surrounding words using the dot product. It uses geometric alignment to calculate exactly how much attention or context one word should draw from another.
Wait, I want to pause and emphasize that insight because it's massive.
Yeah.
We are using pure geometric alignment in space to mathematically quantify semantic meaning and human context. That is the magic of the dot product.
It really is.
But what happens if we want to look at our entire data set differently? We've talked about stretching space and checking alignments, but what if the mathematical grid we're using to measure everything is just fundamentally the wrong grid?
This brings us to the concept of coordinate transformation, or changing our perspective. Sometimes the problem isn't that the data is hopelessly tangled, it's just that we are looking at it from a terrible angle.
Let's use a landscape photography analogy. Imagine you are hiking, and you want to photograph a complex rock formation. From the specific spot on the trail where you are standing, it just looks like a chaotic, messy jumble of boulders. You can't see any overarching structure.
It's just noise.
Just noise. But if you walk off the trail, hike up a nearby ridge, and rotate your camera to view the exact same rocks from a 90-degree angle, suddenly the chaos makes sense. You see the distinct layers of a beautiful, deep canyon.
In that scenario, the rocks did not move. The data points remained exactly where they were in physical space. What changed was your coordinate system. Your perspective shifted. Matrices have the ability to perform this exact same operation on data. They can rotate the mathematical grid itself around the data points.
Let's apply this real-world perspective shift to our engineering pipeline. By default, our data is plotted on a grid defined by our raw variables. The x-axis is income, the y-axis is age, the z-axis is credit score. From this default angle, the data might look like that chaotic jumble of rocks. It's hard for the algorithm to extract a pattern.
But by applying a specific transformation matrix, we can rotate our axes. We change the basis vectors of our space. Now, we are no longer measuring the data against the arbitrary raw variables. The matrix rotates the grid so that the new axes align with the natural shape of the data itself.
So we get a better view.
Exactly. Our new x-axis might perfectly track financial stability, while our new y-axis tracks credit risk.
So when senior engineers talk about finding the optimal representation of the data, they mean mathematically rotating the camera until the patterns become obvious. And this is exactly what principal component analysis, or PCA, does.
Yes. PCA is an algorithm designed to automatically find the absolute best camera angle for your dataset. It looks at the cloud of data points and calculates exactly how to rotate the coordinate system so that the maximum amount of variation in the data is spread out along the new axis.
But calculating how to rotate that space requires us to identify the natural geometry of the data. When we start rotating and stretching space across dozens or hundreds of dimensions, it seems like everything would just descend into chaos. How does the model keep track of the structure of the space when everything is warping?
That brings us to one of the most notoriously intimidating topics in linear algebra: eigenvectors and eigenvalues.
They absolutely have a reputation for being terrifying. The terms sound like incredibly dense academic theory.
They do. But the concept is actually very intuitive once you visualize it.
The word eigen is actually German. It roughly translates to own or characteristic or particular.
Which is actually a very helpful translation. An eigenvector is a characteristic vector of a specific matrix transformation. Let's build a clear mental model of this without getting bogged down in the formula. Think back to our uniform grid. When a matrix supplies a transformation, stretching, squashing, shearing, almost every single data point gets knocked off its original path. If you draw an arrow from the origin to a point, and then you shear the space, that arrow is going to rotate and change its angle.
Right. You take a rubber sheet with lines drawn all over it, and you grab the corners and stretch it diagonally. Almost every single line is going to change its orientation.
Almost every line. But during a linear transformation, there are special, stubborn directions that behave differently. These specific lines might get stretched out, making them longer, or they might get squashed, making them shorter. Sometimes they even flip exactly backward. But the one thing they do not do is rotate.
They stay locked in.
They stay perfectly anchored on their original span. These unrotated invariant lines are the eigenvectors.
They are the anchors of the transformation. No matter how violently the matrix warps the rest of the geometric space, these specific vectors hold their directional ground. You can think of them as the natural, hidden skeleton of the dataset's transformation.
And if the eigenvectors are the specific directions of that skeleton, the eigenvalues tell us the magnitude. They tell us how much the space was stretched or squished along that specific stubborn direction.
If we have multiple stubborn directions that don't rotate, how does the model prioritize them? How does it know which ones actually matter?
It looks entirely at the eigenvalue. The eigenvalue is essentially the importance score for its corresponding eigenvector. If an eigenvector has a very large eigenvalue, it means the matrix stretched the space tremendously in that direction.
It pulled the data apart.
Exactly. In the context of data, a massive stretch means there is a lot of variance along that axis. The data is highly spread out, which means there is a lot of rich information and signal captured in that direction.
Conversely, if the eigenvalue is tiny, say 0.01, it means the space was violently squashed flat along that specific unrotated axis. The data points are all crushed together. There is almost no variance, which means there is virtually no useful information. It's mostly just statistical noise.
This is exactly how PCA makes its decisions. PCA computes the covariance matrix of your data, finds these eigenvectors, which are the natural axes of the data, and then looks at their eigenvalues to rank them by importance.
Which perfectly transitions us to the practical application of this, dimensionality collapse. Or, to use a geometric analogy, casting a shadow. Once PCA ranks these directions by their eigenvalues, what do we actually do with that information?
We use it to ruthlessly delete data, but in a mathematically optimal way. When we throw away the eigenvectors that have tiny eigenvalues, we are intentionally reducing the dimensions of our dataset. We are dropping the axes that don't contain meaningful variance.
Let's visualize how dropping a dimension works geometrically. Imagine you are shining a flashlight on a 3D object, like the coffee mug sitting on my desk right now. The shadow that the mug casts on the flat wall behind it is strictly two-dimensional. By casting a shadow, we have forced a dimensionality collapse. We took a 3D space and compressed it down to a 2D space.
In doing so, you permanently lost a dimension of information. You lost the depth of the mug. You cannot look at the shadow and know how thick the ceramic is.
However, because we cast the shadow from a good angle, a high variance angle, we preserve the primary recognizable structure of the object. You can look at that flat 2D shadow and still instantly recognize, yes, the shape of the handle is there, the cylinder is there, that is a coffee mug. We threw away data, but we kept the core pattern.
That is precisely how dimensionality reduction works in machine learning pipelines. We mathematically project high-dimensional data onto a smaller, lower-dimensional subspace.
But let me push back on this because this sounds risky. If we are intentionally throwing away dimensions, like collapsing a 100-dimensional data set down to 10 dimensions, are we risking throwing away the exact edge case data that might be crucial for predicting something rare? For example, if I'm building a fraud detection model, couldn't the tiny variance in a seemingly unimportant dimension be the exact subtle signal of a highly sophisticated cyber attack?
That is a phenomenal engineering question, and it highlights the constant tension in machine learning, the bias-variance trade-off. You are absolutely correct that when you reduce dimensionality, you're permanently destroying information. If an incredibly rare edge case only manifests along an axis with a tiny eigenvalue, PCA will erase it.
So why do we do it? Why take the risk of losing the edge cases?
Because of the curse of dimensionality. When you operate in massive 1,000-dimensional spaces, the volume of the space becomes so unfathomably large that your data points become incredibly sparse.
Yeah.
Everything is far away from everything else.
So the model gets confused.
Very confused. This makes it exceptionally difficult for models to generalize. They end up overfitting to the noise in those minor dimensions rather than learning the actual signal.
So dropping those dimensions is actually a feature, not a bug. It acts as a form of regularization. By throwing away the low-variance directions, we are stripping out the static and the noise, forcing the model to focus only on the dominant, undeniable patterns.
Exactly. And beyond the mathematical benefits, there are brutal computational realities in the industry. Training a deep neural network on a 1,000-dimensional feature vector requires an exponential amount of server memory and compute time compared to a 50-dimensional vector. By applying PCA, you might compress the data by 95%, retaining the principal components that explain 99% of the variance.
It's the ultimate optimization hack. You preserve 99% of the critical insight, but you slash your computational cloud costs and training time to a fraction of what they were.
We have covered stretching, rotating, shearing, and collapsing space. But to complete our foundational understanding of matrices, we must discuss the most counterintuitive transformation of all. This is the identity matrix.
I like to call this the do-nothing machine. It seems like a complete paradox. We just spent all this time exploring how matrices are incredibly powerful engines designed to warp space and extract latent features.
Yeah.
And then mathematicians codified a specific matrix that is explicitly designed to do absolutely nothing.
It leaves every single vector exactly where it started. It doesn't rotate, it doesn't stretch, it doesn't shear.
It's the matrix equivalent of applying the normal filter to an Instagram photo. It's an option on the menu, but it literally doesn't alter a single pixel. Mathematically, it operates exactly like multiplying a number by 1. 5 times 1 is still 5. A vector multiplied by the identity matrix remains the exact same vector. So if it doesn't do anything, why does it exist? Why do machine learning engineers care about a machine that refuses to operate?
Because sometimes doing nothing is the mathematically optimal choice, and the model needs a safe mechanism to choose that option. The most profound example of this in the history of deep learning is the development of ResNets, or residual networks.
This is a huge industry application. Before ResNets, researchers were hitting a wall. They figured that if a 10-layer neural network was good, a 50-layer network should be better. But when they tried to train incredibly deep networks, the performance actually got worse. The models completely broke down.
They suffered from the vanishing gradient problem. As the data passed through dozens of matrix transformations, the signal got so mangled and compressed that the network couldn't learn anymore. Every layer was forcing a transformation, even if a transformation wasn't needed.
So how did the identity matrix solve this?
The researchers introduced skip connections. They altered the architecture so that a layer didn't just have to output its transformed data. It could output its transformed data plus the original unaltered input data. They essentially gave the network an escape hatch.
A way out.
Yes, they told the network if warping this data is going to destroy the signal, you can easily default to the identity mapping. You can just pass the data straight through, completely untouched.
By giving the neural network the ability to easily learn the identity matrix, the ability to choose to do nothing, they instantly solved the degradation problem. Suddenly, engineers could train networks with hundreds of layers instead of just a dozen. It revolutionized computer vision.
It is a profound engineering lesson. Before you start warping and twisting data, you must ensure your system has a stable baseline. The identity matrix provides that do no harm baseline.
Okay, this has been an incredibly dense and rewarding journey through geometric space. As you prepare to take these concepts into real-world projects, the most critical skill you can develop is the ability to map the dense mathematical jargon to the intuitive geometry we've discussed today. Let's do a quick translation drill. I'll play the role of the host, and you play the senior engineer.
That's fun. Let's do it.
All right, the senior engineer says, we applied a linear transformation to the input space.
Translation. We reshaped the feature space by stretching or rotating the grid to untangle the data.
Perfect. Next one. The weight matrix multiplies the feature vector in the first hidden layer.
Translation. The model mixes the raw features together to create brand new, more predictive composite features.
Nice. How about this one? We reduced the dimensionality of the dataset.
Translation. We systematically compress the data into fewer directions to remove noise and save compute power.
Okay, last one. The first principal component explains most of the variance.
Translation. We found the one single camera angle that captures the maximum amount of information in the entire dataset.
That geometric intuition is what separates a practitioner who just blindly copies code from a tutorial from a true AI engineer who deeply understands the mechanics of their models.
Which brings us to our final synthesis. The ultimate takeaway for you today is a shift in mindset. Machine learning models do not read data passively. They don't look at a spreadsheet and try to parse the numbers. They actively, aggressively transform the geometric space where that data lives. By applying matrices to rotate, stretch, shear, and compress the grid, they force the invisible patterns to become visible. They massage the tangled mess of raw data until the complex boundaries become simple, straight lines.
But there is a massive piece of the puzzle we haven't solved yet. Today, we saw how space transforms. We learned the mechanical operations of the matrix. But if a matrix is initially just filled with random numbers, its transformations will be useless. It will just scramble the data. To truly build artificial intelligence, the model must learn which specific transformations actually work. It must learn the perfect matrix weights on its own.
Which perfectly sets up our next deep dive. In Module 5, we are going to explore how models descend. We're going to dive into the mathematical engines of optimization and gradient descent.
We will finally look at how the model measures its own mistakes and how it uses calculus to incrementally adjust every single number inside its matrices.
We will see how it navigates the mathematical landscape to find the perfect spatial transformations entirely on its own.
You will finally see the mechanics of how the machine actually learns. Before you go, I want to encourage you to actively practice this geometric mindset. Try taking a complex ML paper or an advanced Python tutorial, and as an exercise, mentally translate the linear algebra operations they mention into the physical, spatial manipulations we covered today.
It will completely change how you read those papers.
If you hit a wall, or if you have specific questions about how matrix multiplication or PCA applies to the dataset you're currently working on, write your questions in the comments below. We genuinely love reading them and helping you untangle those concepts. And, of course, to keep building your industry-ready skills and to ensure you don't miss our upcoming deep dive on gradient descent, be sure to like, share, and subscribe to the 60 Seconds Academy channel. We will see you in the next deep dive.